All right, let's get right into it. Today, we're going to break down the fundamental rules that run our entire universe. We're talking about everything from a bus pulling away from the curb, all the way up to how planets stay in orbit. This is all about the core ideas of motion, force, and gravity. So, let's kick this off with a question about something I guarantee you felt. You're sitting on a bus, it's not moving, and then the driver hits the gas. All of a sudden, you feel like you've been thrown back into your seat. So, what is actually happening in that moment? Well, the answer to that question is a really fundamental principle in physics called inertia. Honestly, the best way to think about it is as the universe's own law of laziness. It's this built-in resistance to change. So what does that really mean? It's pretty simple, actually. Objects just like to keep doing whatever it is they're already doing. If an object is just sitting there, it wants to stay sitting there. If it's already moving, it wants to keep moving in a nice straight line at the same speed. That property, that resistance to changing its state, that's inertia. Okay, let's connect this right back to that bus. Your body is just sitting there, minding its own business, obeying this law of inertia. It wants to stay put. When the bus lurches forward, the bus is actually moving out from under you. And for just a split second, your body tries to stay in its original spot. That resistance, that's the backward jerk you feel. And once you know what to look for, you see inertia everywhere. You know, when you beat a dusty carpet, you're moving the carpet really fast, but the dust's inertia makes it want to stay put. So the dust kind of just hangs in the air for a second and it falls out. It's also the exact same reason why they tell you to run for a few steps. If you ever have to jump off a slowly moving bus, your body's inertia is still carrying you forward, and running just helps you match that speed and slow down safely. Okay, so if inertia is this cosmic laziness, this resistance to change, then how do we get anything to, well, change? The answer is force. A push or a pull is what you need to get something to start moving, to stop, or to change direction. And thankfully, Newton's second law gives us the perfect recipe for how force, mass, and acceleration all relate to each other. This incredibly simple-looking equation, F equals ma, is basically the engine of all classical mechanics. It's so powerful. It tells us that the more force you put on something, the faster it accelerates. But it also tells us that if you use the same amount of force, a heavier object, one with more mass, more inertia, is going to accelerate a lot less than a lighter one. This is how we actually measure a change in motion. Now, Newton's third law is what really completes the picture. It says for every single action, there is an equal and opposite reaction. Forces always come in pairs. You know, a racket doesn't just magically go up. It pushes hot gas down with an incredible amount of force, and that gas pushes the rocket up with the exact same amount of force. When you swim, you push the water backward, and the water pushes you forward. It's a beautiful, universal dance of interactions. So we've gone from everyday pushes and pulls to these fundamental laws. Now, let's scale way up. Let's talk about the biggest force of them all, the one that's invisible, that's everywhere, and that literally holds the cosmos together: gravity. This is such an elegant rule for how everything works. It's the reason an apple falls from a tree, and it's the exact same reason the moon orbits the Earth. It's simple, really. More mass means a stronger gravitational pull. But more distance between things means that pull gets weaker, and it gets weaker fast. And this number right here, this universal gravitational constant, or big G, well, that's the secret sauce. It's this incredibly tiny number that is the same absolutely everywhere in the universe, and it sets the strength for all of gravity. And you know, its tiny size is exactly why gravity feels so weak to us day to day, even though it's powerful enough to keep entire planets in their orbits. And that leads to this just fascinating paradox. Gravity is strong enough to hold galaxies together across billions of light years, and yet it is by far the weakest of the four fundamental forces of nature. I mean, think about it. A tiny little refrigerator magnet can overcome the gravitational pull of the entire Earth just to hold up a piece of paper. It's pretty wild. All this talk about gravity leads us directly into one of the most common mix-ups in all of physics. And it's something we all get wrong in conversation all the time. And that's the difference between mass and weight. So here's the deal. Your mass is the amount of stuff you are made of. It's a constant. It's the same whether you're here on Earth, on the moon, or just floating out in deep space. Your weight, on the other hand, is not constant. It's just the force of gravity pulling down on your mass. So if you go somewhere with less gravity, like the moon, your mass stays the same, but your weight goes way down. And if you really want to feel this difference, there's no better place than in an elevator. When that elevator starts accelerating upwards, the floor pushes up on you harder than normal, and for a moment, you actually feel heavier. And when it accelerates downward, you feel lighter. Your mass never ever changes, but what you feel, your apparent weight, is all over the place. So, after all that, what's the big picture here? What's the main idea we should walk away with from this explainer? It really does all connect, doesn't it? Inertia is the default state. It's the universe's tendency to just keep things as they are. Force, which we define with F equals ma, is what causes change. Every single one of those forces is part of a perfect action-reaction pair. And gravity? Well, gravity is the ultimate long-range force that orchestrates the entire cosmic dance. So really, from the inertia that's keeping you settled in your chair right now to the force of gravity that's holding you to the Earth, these principles are everywhere all the time. Understanding them is really the first step to seeing all the incredible hidden physics that are happening all around us.